now the next thing is, having gotten this, now let's just sort of give an overview of the 4 main families of algorithms that we will talk about in this course. Okay, so let's the basic philosophy always is, you know, start from some point x0, okay, then you are going to undergo a sequence of iterations, okay. So let's call this iterations. Very, very rarely would you have a case where you go from start to the solution in one shot, okay. That happened in high school problems, not in real life engineering, okay. And hopefully you'll end up at the solution extra, okay. Now what distinguishes all of these algorithms is how you go from xk to x of k plus 1. That's where all the details differ, okay. And as I've mentioned to you, there are 2 families over here. One is called line search and the other is called trust region, okay, broadly. So our overall optimization of going from x0 to x star, when I talk about the real nuts and bolts, what is it? Going from xk to xk plus 1, right? So if I write it like this, supposing this is my xk, I'm standing over here, here is xk plus 1, right? We are in a vector space. That means, for example, xk and xk plus 1, these are n-dimensional vectors. That means between these 2 points, I need to specify 2 things. One is a direction and a length, right? That's how I will get from here to there. So this direction, I can give it a symbol p of k, and how much I should walk along this direction is going to be, the common symbol for it is alpha k. So this is, you can think of this as length and you can think of this as direction, right? Having done this, I get a chance to show you formal notation in optimization which is used a lot. So what is this whole thing? Okay, let me write it down. I have xk plus alpha k pk. I am at xk, I don't know what pk to take and I don't know what alpha k to walk. So my optimization process is a journey or a process to find out alpha k and pk. So those are the variables of my optimization, right? So I will write this as minimize. So when I write min, it means minimize whatever is to the right of it. So minimize this. Below the word min, I should write down what are the variables of my optimization. So what are the variables of my optimization? Alpha k and pk. Alpha k, pk. Okay. So if I just write min this, it would mean minimize this whole thing. You may have seen this notation written in a lot of papers, and now you know what that means. The variables of optimization are below, the objective function is to the right of min. This is what it means. There is another related thing that you will see, you will find argmin. Now what does that mean? It means basically arg means arguments. So what are the arguments to this objective function? They are basically alpha k and pk, and you would write this as alpha star p star equal to this. So the optimization problem was to minimize, but at each step I need to solve this optimization problem. Argmin means tell me what are the arguments that which minimize this function. They would be alpha star p star, which would get I mean, those are the alpha star and p star that I use to go from xk to xk plus 1. That is the meaning of this. So whenever you see a textbook or a paper saying min or argmin, look for what is below. Those are the knobs in your hand. Nothing else can be changed. For example, notice xk was not in my hand. Why? Because My algorithm has found itself at xk. It's given to me, I cannot change it. What I can change is where I go from there. So I have a freedom in choosing pk. I have a freedom in figuring out how much to walk along that. And my first order, second order theorems are going to help me figure out these directions and distances. Okay, so that's the name of the game. Okay. So, so we'll start by talking about line search algorithms because they are the most popular algorithms. In fact, what everyone loves these days, machine learning, takes one of those members of that family. Okay, so line search algorithms. Okay, these essentially correspond to different choices of pk. The first and the simplest is the steepest descent or gradient descent. The two mean the same thing. And over here, you don't try to find out pk at every step, you take it as a recipe, and I take this to be equal to the negative of the gradient. Okay, this is your steepest descent or gradient descent algorithm. Okay, why we choose this, I will prove it to you shortly. Okay. This is the first one. The second one is very powerful, which is called the Newton method. Right. In this, again we will prove it. I will note down the expression that you have. It is the Hessian comes in with an inverse. So inverse of the Hessian multiplied by grad fk. Oops. But this is not enough. You also need the Hessian to be positive definite. Okay, these are that's why I've written it as an AND condition. If the Hessian is positive definite, then you can plug in this expression and get your pk. The third method was invented because the second method ended up being very expensive. If I have a function of many variables, calculating second order derivatives can become very computationally expensive. So people came up with tricks to approximate the Hessian. So therefore the word is self-explanatory. They're called quasi-Newton methods. For all points where you're running the iteration. Right, so the quasi-Newton method, basically what it does is that instead of working with the Hessian, it will do something like this. Okay, so what is this bk? Bk is essentially a cheaper approximation of the Hessian inverse. Okay. Now, just one word of why this Newton method is very popular. We will state this as we develop it more in detail. The rate of convergence. Remember, we had spoken about the rate at which sequences can converge. Turns out that the Newton method has a quadratic rate of convergence. Okay, whereas the steepest descent has a linear rate of convergence. So that can mean the difference between hours and minutes in your simulation or your problem getting solved. Right, so this is quadratic. So if you have a high performance computing cluster where you can compute Hessians, use it. Don't go for gradient descent. right? And the fourth method is something very interesting. It is based on the first order method, but much more clever than a first order method. Okay, many of you may have heard of it. It's called the conjugate gradient method. We will spend a fair amount of time on this conjugate gradient method as well. Here the cleverness comes from how I choose my pk. The pk, if I just wrote this as this negative gradient, it becomes gradient descent. What is clever is that it doesn't take just this, it modifies it from the previous direction it had been in. So it writes it as a linear combination of the negative gradient and okay. Now how we choose this beta k is, there's a lot of very elegant and clever math over here, and this gives us a little faster rate of convergence than the conjugate gradient. The other great advantage of I mean methods 1 and 4 are that they can easily be generalized to nonlinear methods, nonlinear functions, non-convex functions and so on. Okay. All right. Right. Any questions so far? Okay. Now, we've mentioned everywhere different choices of pk, right? We want to find out what are there any restrictions on how we can choose pk, how do we design pk? These formulas are given to us, we will derive them. But before we go to that, let's just write down a little bit more rigorous conditions on what this pk should satisfy, right? So these are what are called descent directions. And we are talking about the requirements on them. Descent is clear because if I'm at some point I want to minimize it, I need to go in a direction where there is a descent of the function value happening. So they are called descent direction. Okay. The first condition is that the direction of, we will prove this, the direction of steepest descent. Anyone wants to guess? Negative gradient. This is if you were in a hurry to climb down a hill, for example. Literally, take the example of a hill. If you are climbing a hill, right? So let's draw a hill. So the hill. Let's say this is a contour of constant height, right? And you wanted to, in this case, let us say climb the hill as fast as possible. Should you go along this direction? Obviously not. If I go along this, I'm at the same height, right? Where is the rate of change of the hill height the maximum? Right? It's going to take me over here. Right? So this is as fast as I can go. Right? So this is the direction of steepest descent is negative gradient, right? What we will find out a little counterintuitively as we go further, particularly when we study the conjugate gradient method, we find out that actually going in the direction of steepest descent is not always the best of ideas. Sometimes you can get to the solution faster if you don't choose the direction of steepest descent. This is counterintuitive, but we will show it rigorously. So anyway, this is our the first condition. The second condition of for second requirement for descent direction again is intuitive. If I didn't want to go in the fastest route to the top, but I'm happy taking some route, can you make any comment based on this diagram of what should be allowed in terms of, think of angles between vectors. So this was, for example, negative gradient. What other directions can you choose? Supposing I choose to walk here. I'm going in the wrong direction. I'm not climbing the hill. So what is the angle now between minus grad f and the red arrow? It's more than 90, right? But if I were on the other hand taking any direction which is like this, it doesn't look as efficient as negative gradient, but I am going in the general direction where my function is, in this case, maximized, right? So that gives us the second condition, which is basically that, pardon me, the inner product should be, yeah, it's related to the inner product, right? So we say that a descent is legitimate Okay, so I hope I didn't confuse you by showing you a maximization problem. Should have, if I wanted to tell you like this, then if this was a maximization problem and this is a minimization problem, right? So if I'm at this point, which way is the gradient increasing? Right? If I go in this direction, the function value is increasing. If I want to decrease it, I need to go in this direction. Right? So anyway, you get the geometric intuition of the angles. We'll prove this rigorously going forward. Okay. All right. So we'll leave that for the next time to show you the proof of this. Okay. And we can pause over here and take questions over here. So let me know what is not clear, if at all. Yes. Very good question. How do we choose the initial point of our algorithm? Any guesses? Random is a strategy. Okay, so this is worthwhile noting because it's actually a very practical problem. How to choose x0? So the first response is choose at random. That's one possibility. What else? What is the most common strategy? You actually start from the origin, right? Initialize your vector with all zeros. What other strategies are there? So here is the place where you get to use your intuition. You need not come up with some very rigorous thing. Sometimes intuition helps you get a good solution. So what else? Pick those points. Okay, that's another thing. So pick randomly, some points. Choose maxima of mod of norm of grad f xk. Is that what you mean? Right. So he's saying that find out of these random points where the gradient is sharpest. This may work, may not work. Right. So I'll give you an example. So let us say I picked my first, this is my function value, I picked my first point over here and I picked my second point over here. Now the value of the gradient is very high over here, right? The function is changing very rapidly in the first point. Here it's much more gentle, right? So what will happen if you choose this is that you will quickly arrive at the solution because the gradient is very sharp, you will quickly descend over here. Here you may make a more leisurely progress to reach this point over here, right? So it is a good strategy. Like most strategies, these strategies don't work when there are multiple local minima. There's no sort of immunity from getting stuck in a local minima. Once you reach here, you're finished. There's no way for you to get out of this valley. You would have to restart your algorithm, pick a new point and see do you get a better minima, right? So but it's a legitimate strategy. Anyone else wants to guess? What else could you do? So, yes. In this example, this is legitimate because I'm leading. If I at that point, if I go in this direction, the function value is decreasing locally. So that's why it's legitimate. Okay, so what he's saying is that once you get stuck in a local minima, you should allow for a illegitimate descent direction so that you start climbing instead of descending, right? Those are more and more band-aid solutions to fix an already bad situation, and many practical algorithms do things like that. Okay, that is fine. But right now the discussion is how to choose a starting point, not what to do once we are stuck. So okay, another thing that you could do, which is a very common strategy, is make a crude approximation of your problem. Okay, instead of discretizing your image into 1024 by 1024, discretize it into 64 cross 64 if your input was, for example, an image, and you get a much cheaper model. Find out the solution to this because it may take much less time, and the solution that you get from that, use that as the starting point in a more accurate model, right? So solve a simpler problem and use that solution to get to x0, right? This is very commonly done because in real life engineering, a realistic optimization, a realistic objective function can be very expensive to evaluate. One evaluation could even take hours. So you may not have the luxury of, just throwing up a whole bunch of random points and choosing which one to go from, right? So solve a simpler problem which instead of 5 hours takes 5 minutes, get a solution and then use that. Another popular, in fact, one of the more intelligent uses of machine learning is use machine learning to give you a good initial guess. Don't use it to solve the problem because then that's black boxing it. People do that also, but if you use it to give you a good initial guess and then a conventional optimization algorithm gives you the solution. So in this example which I have drawn, if you could get a good guess, for example, this blue point is a great guess, whereas this green point is a terrible guess. Why? Because starting from the blue point, I can reach the global minima. Starting from the green point, I will get stuck in the local minima. You see the difference between these 2 points? Now, a priori, you don't know whether the point is good or not. So there is a lot of recent research where machine learning is used to predict a good starting point, and then you sort of use your conventional algorithm and come down to the local minima. Okay. Why this is good is because you are not insisting on ML to solve the exact problem, which may be computationally very difficult. You're just saying, give me something approximately correct, and that works. And that's why I say this is a more intelligent use of ML. Good, I think we've got 5 good strategies. Any other suggestions on how to pick a starting point? Right. So question is that we never spoke about how to choose this guy, right? Alpha K. That's going to be step 2. Step 1 is pick your algorithm out of these 4, which is basically steepest descent, Newton, quasi-Newton, conjugate gradient. These gave me the direction. Next step is figure out what is the optimum length. And we're going to have an entire module on how to choose the optimum length. So you're a step ahead of us. So we need to do that next. Okay. All right. Any other questions? This was a good discussion. Okay. Okay, so that's your strategy for choosing the step length also. Okay, that's a variation of choose at random and do something more. Okay, that's fine. I mean, it's a variation of this. There are many variations of these possible. There's a question at the back, yeah. Why can't we use it for non-convex functions? Ah, good question. Question is, why can't we use, let's talk about the Newton method. Why can't we use the Newton method for non-convex functions? Can someone answer that? Right? For a convex function, I know that the Hessian is positive semi-definite at least. For a non-convex function, the Hessian need not be positive semi-definite. If it is not, then I fail the requirements of the Newton method, and that's why I'll not be able to use it. And we will derive this, okay? You need not take it on faith. We will derive this. It's basically just the use of the second order Taylor's theorem which will give us this condition, okay? That's why I mentioned that for non-convex functions, approaches 1 and 4, occasionally 3 may work. Positive semi-definite at least. Yeah. For convex functions, it's always, that's the almost interchangeable definition of a convex function is that the Hessian is positive definite, positive semi-definite. Yeah. Again, the intuition is a upward opening bowl. Correct. For a non-convex, we'll have many local minima. That's an open research problem. If you have a non-convex function with lots of local minima, that's basically you're asking, the question you're asking is what troubles all ML researchers day and night. That I have a function in 1 million variables, I have gazillion local minima, how do I make sure that I don't get stuck in it? And there are no rigorous strategies for it, there are a lot of heuristic strategies for it. And that's where the state of the art is, and therefore there's a lot of chance to make a contribution also in that.